Okay, so here is Unit 3, Day 5, B. So this is going to be it for the unit. This is the last assignment, last notes, and then we'll get ready for the test for Unit 3. Start out, I want to do some warm-ups here. So I would like for you to pause the video. So give it a pause, try these 3 problems out, see if you know what you're doing. I'm going to write down the work real quick to let you see the right way to do it, but hopefully you got it. Hopefully you get these right. So in fact, if you want to, we could just do this too. I could tell you the answers right now if you want to write those down, and then that'll help you figure out if you did it right. Right number of zeros here. Okay, so there are the answers. Try those out. These are x equals. So give those a try and see if you get the correct answer. All right, here's the work. So check this out. And I think, let's see, where might need some explanation over here. I think this one's pretty self-explanatory. You had 1 to the 4th is your base to the x over 3 power, so I divide by 32 first. And then to get rid of the 1/4, I use a log base of 1/4. And so on, and got 6. This one here gets kind of crazy because it is a common log, so the base is 10. I combined with the addition, which means multiply these together. So x times x minus 2 would give me an argument of x squared minus 2x. On the other side then, I got 8, and when I get rid of that common log, I use a base of 10. When I do 10 to the 8th, that's a big number. So instead of writing out 1 followed by 8 zeros, I just put 10 to the 8th. And then if I bring that over, it'd be a negative 10 to the 8th equals 0. And then I put in the quadratic formula. I didn't do the minus one because this is a huge number. So if 2 minus a big number is going to be a negative, I know that's not going to work up here. If I have a really big negative number, then I take 2 more away, that's not going to work. So I didn't even consider the negative. I only did the positive one. So I added, but I did not subtract on this one. And this was the number I've got. Kind of a crazy number. That's a decimal, but that's fine. We can do decimals on this. And then the last one over here, 2e to the x plus 5e to the x is 7e to the x. So don't forget you can add those as if they're like terms, since they both are being multiplied by e to the x, and then solve like you normally would. Okay, then down here, when we examine data, there are several different methods that we may think when you look at a graph, like, well, it looks kind of exponential, but it could be quadratic too, or it's hard to tell exactly, but there's a few little tricks we can do that'll make it very clear to us. And the biggest thing is the best way, the easiest way to do regression is linear regression. It's like the most basic way. So we'd love to try to find a way to make everything linear if we can. Okay, so linear regression we've done over and over. If you take AP Stats, that's pretty much the only regression you do. You do a little bit of re-expression, but not a ton of it. But you mostly do linear. There's so much stuff that can be done with linear that you can really dig deep into it. But we do notice that if you have logarithmic regression, and specifically natural log regression, if you take the x's and y's, you take the natural log of the x's, compare that to the y's, if it's linear, if those dots are very linear and it has a very high R value, that means the original data was logarithmic. We know that or we've discovered, or mathematicians have discovered, that if it's an exponential regression, then when you take the natural log of the y and compare it to the x, it actually straightens it out. So instead of having that exponential curve, it's going to make a straight line out of it by taking the natural log of the y's. Okay, and you get an exponential regression. And in the power regression, if you remember power regression, that's where you have the base is x and you take it to the same power. So like you start plugging in numbers, like you have 2 squared, 3 squared, 4 squared, 5 squared. The exponent stays the same, but the base changes. That's a power regression. It's different exponential. With that exponential, the base stays the same, the power changes. Here, the base changes and the power stays the same. But on that one, if you take the natural log of both x and y and then re-graph it, it makes a straight line. if it's a power regression. So it's kind of a cool way to check, like, is it really an exponential? Well, I'll take the natural log of y's and I'll run a linear regression. If it's a really high r value, an r squared value, then yeah, it was exponential, and so on. So down here below, we're going to look at AIDS cases. Okay, so this, you guys are living through a pandemic right now. You know, when I was a kid, I won't mention which one of these years, but I was born in one of those years. There was an AIDS epidemic. So epidemic isn't quite as big as a pandemic. Unfortunately, AIDS, you know, obviously you know which ways it could be transmitted, but it was not, you couldn't transmit it by breathing on each other like COVID is. So it wasn't nearly as contagious, but it is much more deadly than COVID too. So it was a pretty serious thing. In 1982, there were 434 cases in the United States, and you see how that drastically increases here. We're trying to figure out what kind of regression is this. We can pretty much tell it's not linear because it isn't as x goes up, y goes up by the same value. Okay, it's not exactly the same every time. Like here, this is a 3,000 increase. This is about a 1,000 increase. Well, if it was linear, it'd be about 1,000 every time, or it'd be 3,000 every time. So first, let's enter the stats into your calculator. So go to your stat edit, put these in your list, put this data in, and use 82 for 1982, and so on. And we're going to make a scatter plot. So I've got that data in my calculator. So try that out. Put it in the calculator. Remember, we'll make a scatter plot, a stat plot out of this. Got L1, L2, got everything I want. Zoom, and we're going to use 9. And you look at that and you say that it's probably exponential, you know, from what we're talking about. You know, of the ones we said, it's not linear, it's not a natural log. Natural log bends the other way. Could be a power regression, or it could be exponential. Okay, I'm not sure where that other line came from. Let me get rid of this guy. Delete these guys. I think that's from stuff we're going to do on the back. So we're going to dig a little bit deeper here. Okay. But step 2 says that the data looks exponential. So if it is exponential, then when we take a log, that's going to undo the exponential part, and it's going to flatten it out. It's going to re-express it linearly. So to take the natural log of the y values, so I want to, because up here it says if it's exponential, take the natural log of the y values, and you'll get a straight line out of it. You'll linearize it. So let's go to the data here. Whoops. And if you remember, we had this on another video. We're going to take the natural log of the y values. These are the y values. L2 is the y values. So we're going to go to the top of L3, make sure L3 itself is highlighted, and we want to type in natural log L2. So what it's going to do is take all the L2s, it's going to take the natural log of them and put the new data down here. So it's almost like putting a formula into Excel. So natural log of L2. And then there's all the natural logs. Now find the line of best fit for this data. So we're going to do linear regression for the original x's and the new y's. Okay, so this is x comma natural log y. Okay, so go to stat, over to calc, and we want to do L3. We don't want to do L1. We want to do, I'm sorry, we don't want to do L1 and L2. We want to do L1 and L3. I'm going to store it in here. I'm going to put in Y1. I always like to do that just in case. We're going to go look back at it later. And now hit calculate. And we want to type this out. Now, this gets very picky. So we want to go to a few decimal places here. So I'm going to go out to about 3 decimal places on this one, I think. So careful writing the equation. I'm going to say, I don't want to necessarily put y equals ax plus b, because remember, I took the natural log of the y's. So when I take x, on this one, when I took x, I plugged in x, the thing that came out was the natural log of y. So I'm going to put in natural log of y equals, and my a is 0.788x plus, and then my b, actually, let me change that. Got some white out there. So minus 58.296. I'm actually going to go one more, 7. I'm going to go way out there on that one. If you change your decimals just a little bit later on, that can affect things quite a bit. So anyway, So there's my equation. This would tell me, using the original data, if I plug in 82, I take it times 0.788, I minus 58.297, that's going to equal the natural log of y. So if I took e to the that power, what comes out would be y, which is going to be about 434. Okay, so this is giving me the data. It's doing it in a linear equation though, but we just have natural log of y there. Now I never found the exponential model. I found the linear model, but I can actually use this to find the exponential model. Okay, so I'm going to rewrite that. So natural log of y equals 0.788x minus 58.2967, and I want to write exponential, which means I want to get rid of this natural log. I want y by itself. Well, how do you get rid of a natural log? We use a base of e. So I'm going to take e to this power and e to all of that power. Now, left side's the easy one. The left side comes out to be y, just y by itself. The right side is where it gets a little ugly. But if you remember, if I am, well, maybe think of it this way too. Think of this as plus negative instead of subtraction. And if we have a plus there, if you're adding the exponents, you could actually split it as two different e's as multiplying. So think about, remember how if I had x to the a times x to the b, that's the same thing as you add the exponents a plus b. Well, I can go backwards with that. If I have x to the a plus b, or I have e to this plus this, I can split them with multiplication. So they have each have their own bases. So I'm going to have e and e with different exponents. So this one's 0.788x. This one over here is negative 58.2967. Okay. Another property, or exponent property, if you have powers being multiplied. Remember, if I had x to the a b, that's the same thing as x to the a times b. We'll go backwards with it. If you're multiplying them, you actually split them up and say that one's the power. Well, here I'm going to say that this is the inside being raised to the x power. Okay, so I'm going backwards. A lot of those exponent properties, we went one direction. Now we're going the other direction with them. So now, and when we're doing exponentials, we want to have the go back here. So we have the initial value and then the number that's being raised to a power. So like this is the growth or decay factor. That needs to go second. So right now the one with x needs to go second. So I'm going to rewrite these. I'm going to flip-flop the answers. Type this into the calculator. When you type this into the calculator, you're going to look at that and say, that's basically 0. But remember, the exponentials, you can't have a 0 in there. We don't want a 0 because we're going to be multiplying everything. If we took 0 times anything, if we have initial value 0, then it's a flat line. It's y equals 0. The whole thing wipes out. So I do want to be specific with this. I'm going to say 4.809 times 10 to the negative 26, which is a very tiny amount. We're starting with a very small amount. And basically what this is saying is if this is 1982, we're seeing how many AIDS cases existed in 1900. And that's why it's such a small number. Okay, I mean, maybe if we went back and made this like year 0 and then 1983 year 1, this would be a much more realistic number. But essentially in 1900, there weren't any cases of AIDS, probably. I have no idea, but I doubt there were many. So that's why it's such a small, tiny number. Now this over here, so e to the 0.788 power, I get, so 2.199 to the x power. Okay, so basically every year that passes, it was going up by more than double. It was more than doubling every time. Okay, and now if you compare these two guys, if you plotted that, it's not going to be perfect because these decimals are so far off, and we're starting at year 1900 and going on up. But let's look at this graph here. So I typed in, so this one up here was the linear version of it. Here's our exponential. Now when I graph that linear, it's going to make a straight line. That's okay, we can kind of ignore. In fact, I'll just do this, I'll shut that off because that's just going to be a straight line that doesn't have anything to do with the data we typed in. The data we typed in is logarithmic or exponential. But how does this match up with that? And it's going to be pretty close to that data, but remember, because of these decimals, it's going to be a little bit off. Let's graph it, and it's going to fall pretty good for a while. Notice it didn't do too bad, actually, a lot better than I thought it would. And it goes up this direction. Okay, so that's the exponential equation, exponential model that we did based off the linear model that we made. So it all ties together. I mean, it convert back and forth from linear to exponential and vice versa. Okay, so let's go to the backside now. We're going to do a little bit more, and I do want to go a little bit faster just to, because the video is getting kind of long here, 15 minutes. But we're going to do the same kind of faster idea though. Type this data in, take a look at it. Okay, so pause your video, type that in. Okay, so we got our data in there, so enter stats in the calculator, look at the scatter plot. Let's go zoom 9 on this guy. And again, it doesn't look a whole lot different than the last one. It looks like it's definitely not logarithmic. I'm going to throw that out right now. So based on the graph, what type of function do you think? Okay, so this definitely looks exponential, but it could also be a power function. Okay, because power functions work like that too. They kind of curve up like that. Now exponentials go up really fast. Power functions don't go up quite as fast most of the time on that. So let's look at, so it's one of these guys. I'll just kind of circle both of these and put a question mark. Looks like one of those. So let's check the models and see. So I'm going to type all three of these. I'm going to do stat over to calc. And I'm going to go down to, and logarithmic is natural log. We're just going to do log. We're going to do natural log, then do exponential, and then do power. So do these three and write them down. So pause your video and try that. Okay, so here's our equations. Hopefully you can check them out, pause your video to check those out, see if they're pretty close. But the big thing here, kind of what we thought would happen, the logarithmic had the lowest R value, so we're pretty sure that's not going to be it. We could tell from the data it wasn't logarithmic, didn't have that curve going this way. But it looks like it was more of a power function because 0.996, that's a pretty good fit. So we're going to go back and say it was a power function. Whoops, cross this, so circle that and cross that out. It's more of a power function than anything. Let's see the last guy now. It says the following data was recorded in a lab. Has to do with detergent and all kinds of other stuff. So we're going to put this data in and use the method above to write an exponential equation for the data. So I'm going to let you guys do that. You can type in the calculator, again, do exponential regression, and it's I'll just put the answer down, but definitely try it out. Make sure you know how to do it. If you're pretty confident you know how to do that, you can probably move on. Letter D, or example D and E now. Rewrite each exponential linear function as an exponential function as an exponential function in the form y equals. So no, these are. So we want to linearize using. Sorry, we got this back here. So linear, and we're using this form to go that direction, but we want y equals ax plus b. Directions are all messed up there. Sorry about that. So linearize using the natural log. So we want to use the natural log to make it look linear. And if you look on the front of your paper there, somewhere in this area, it has these guys here. And if, exponential, you have the c and the d, where c equals e to the b, and d equals e to the a. Well, a and b is what I'm looking for to write my a and b. Okay, so if c, in this case, my c, which is e to the b, happens to equal 1.7. So if I want to solve for b on this, I want to take the natural log of both sides. So natural log of e to the b equals a natural log of 1.7. So b, in this case, b, if I take the natural log of 1.7, I had it written down here. Where did I put it? Well, I'll just redo it. I had it written down in my notes, but so natural log of 1.7 is 0.531. Okay, so that's your b, that's your number on the end, and then here the d, so the rate equals e to the a, which is 5.6. So if I want to find a, take the natural log of e to the a, the natural log of 5.6. So a is going to equal 1.73 x. So, I'm sorry, 1.73. Where did I go wrong here? To the x. Oh, here we go. So this was d to the x would equal this to the x. And if I bring the x out front now, so x times a equals 1.73x. That's why this is being multiplied by x here, which just so happens to be a to the x power here. So that all works out. So y equals 1.723x plus 0.531. Again, a is a number that goes here, b is a number that goes there. Okay, so but the same thing here, we're going to do the same idea here. Instead of saying that, instead of using e in natural log, we're going to use a base of 10. So I'll say a is going to be, wait a second here. So c, which is 2.58, is going to equal 10 to the b. So instead of e to the b, it's 10 to the b using base 10. So c, if I want to get rid of that 10, it'd be log, common log of 2.58. So I'd get b by itself, which equals, erase this, equals b. So b equals, I'm going to write this down. I had it all written down. I can't remember which one it was. So look, the natural log, sorry, the common log of 2.58. And I apologize, my video stopped recording. I ran out of memory, so I ended up finishing this. But when you took the common log of 2.58, you get 0.411. And then the d, which is the 0.97, the growth factor, that I'm going to make that a 10 to the a, so I'm going to use a common log to solve for a. So common log 0.97 is negative 0.013. That gives me this linearized problem. And then down here for e, this is kind of more practice what we did on the front. So I'm going to try to go very quickly here. This was to get rid of, I want to get the y by itself, so I'm going to take e to both sides. Again, think of this as a plus negative, so it's going to be y equals, and it'd be, remember, if you're adding the exponents, you're multiplying the bases, so it'd be e to the negative fifth times e to the 2, and then think of that as being raised to the x power because it's 2 times x. So y equals, put e to the negative fifth in the calculator, it's about 0.007, and then the base then, e squared is 7.389 to the x power. Okay, same thing here, we're going to get this guy, I want to get y by itself, so the base is 10, so take 10 to both sides. Okay, so this would be, since we're multiplying these, I can write two different bases. I'm going to put the 6 first and then put 3 to the x power because I need an x as a power. So this is going to be a huge number. So y equals 1 followed by 6 zeros, which is 1,000,000, times 1,000 to the x power.